1 terabit per second. That's the number a team of Chinese engineers hit inside a lab, and it's now sending ripples through the entire tech industry. In plain terms, that's fast enough to pull down 20 full-length movies in less than 1 second. Not 20 minutes. Not 20 seconds. Under 1 second. Meanwhile, the 5G phone sitting in your pocket right now would need close to 2 minutes to do the exact same thing. So how did a research lab leap 100 times past the fastest wireless technology most of us have ever touched? And here's the part that really matters. This isn't just about raw speed. It's about a completely new way for machines, cars, and robots to communicate with each other. A way 5G was never designed to support. Before we dig into how this actually works, and why it's got telecom giants and entire governments watching closely, let me ask a quick favor. Scripts like this take a lot of digging and a lot of hours to pull together. So if you're getting something out of it, drop a like. It genuinely keeps this channel alive. And subscribe too, because what happens later in this story is honestly harder to believe than the lab number itself. There's a moment coming up where this tech got tested not in a lab, but in a real city, during a brutally humid summer. And what happened there is what turned a lot of skeptics into believers. Let's build up to it, piece by piece, starting now. Why 5G became the standard. To understand why this new breakthrough is such a big deal, you first need to understand what 5G actually accomplished. Because 5G wasn't some minor version bump, it was a genuine leap, and it earned its place as the backbone of modern life. Honestly, you can't appreciate why a network 100 times faster matters until you see how good the current one already is. Here's the basic idea behind it. Shorter radio waves can carry far more data, but they can't travel very far. So instead of relying on a handful of massive towers like older networks did, 5G leans on thousands of small towers packed close together. Picture it this way. Older networks were like a few giant stadium floodlights. 5G is like thousands of small bulbs strung along every row of seats. More coverage, more precision, far less wasted signal. That's the reason doctors can stream live surgical footage between hospitals across a city. What's the reason factories can run robotic arms with almost zero lag? That's the reason more than 1.5 billion 5G connections were active worldwide by 2023, roughly equal to the entire population of India carrying a 5G signal in their pocket at once. Beyond hospitals and factories, 5G reshaped smaller, quieter moments too. It let farmers scatter sensors across huge fields to monitor soil moisture in real time. It let shipping ports track containers without running a single physical cable between the nets, cranes, and the control room. None of that makes headlines, but it shows just how deeply 5G embedded itself into everyday life once it was actually built out. On paper, 5G looked like the finish line. But here's a detail almost nobody brings up. 5G was never meant to be the finish line. It was built as a bridge, an extremely strong one, capable of carrying enormous weight, but a bridge nonetheless. And bridges are built to lead somewhere. That somewhere is exactly what this new breakthrough is reaching for. Understanding what 5G still can't do is the key to understanding why researchers went looking for something faster in the first place. The gap 5G was never built to close. So if 5G is this capable, why do we even need something faster? The honest answer has nothing to do with 5G failing. It's still doing precisely what it was designed to do. The real answer is that the world is now asking wireless networks to take on a completely new job, one that has nothing to do with people streaming videos or scrolling social feeds. This is the exact gap the terahertz breakthrough is trying to close. Think about self-driving cars communicating with each other at an intersection. Think about robotic surgery performed from hundreds of miles away. Think about factories where thousands of machines have to react to one another in a split second. This isn't about humans consuming content anymore. It's about machines making instant decisions on our behalf. Engineers have a name for this: the beginning of the Internet of Intelligence. A network built for machines and AI systems constantly talking to each other, not just for people checking their phones. To picture how different this job really is, compare watching a movie to driving a car. If a movie stutters for half a second, you barely notice. But if a self-driving car takes even half a second longer than it should to spot a pedestrian, that delay can turn into a real disaster. 5G was built for people, and it does that job beautifully. It just was never asked to handle machines making life or death calls in real time. This is where the numbers start to matter. A single 5G tower can reliably support roughly 1,000 connected devices before performance starts to dip. That sounds like a lot, until you picture a mid-sized stadium packed with 60,000 phones, sensors, and cameras all trying to connect at once. That's 60 times overcapacity in one building on one afternoon. The same crowding shows up at airports during busy holiday travel, or in disaster zones where rescue crews need dozens of drones and sensors communicating while thousands of nearby phones are also fighting for a connection. Then there's delay, what engineers call latency. 5G's best-case delay sits around 4 milliseconds, which is basically invisible when you're streaming video. But for a self-driving car reacting to a child stepping off a curb, or a surgical robot operating from far away, those few milliseconds are the line between a smooth save and a dangerous mistake. Doctors who work with remote surgical robots describe the gap simply: a tiny delay that feels like nothing when a web page loads slowly can feel like an eternity when a robotic arm is making a precise cut inside someone's body from hundreds of miles off. This exact gap is what pushed researchers to stop trying to squeeze more performance out of 5G and instead look somewhere entirely new on the radio spectrum. It's a shift that sounds minor on paper, but turns out to be the whole reason a 1 terabit per second lab result is even possible. And it's where our story really starts to accelerate. The frequency nobody could tame. Here's the idea that changed everything. Instead of squeezing more out of the same frequency range 5G already uses, what if engineers pushed much higher up the spectrum into a band called terahertz waves, the space between microwaves and infrared light? For decades, this range was barely touched for communication. This is the exact frequency behind the 1 terabit per second figure we opened with, and getting it to work reliably is the whole reason this breakthrough took years to arrive. To see why this part of the spectrum was so tempting, picture a highway. The frequencies 5G uses are like a busy 6-lane road. It works, but it clogs up fast during rush hour. Terahertz waves are like discovering a brand new 20-lane highway sitting right next to the old one, mostly empty and just waiting to be used. The catch is that this new highway has a strange fog constantly rolling across it, one that most cars simply can't drive through. Why didn't anyone use it sooner? Because terahertz waves have one massive weakness. They get absorbed almost instantly by water vapor in the air. A signal could die within a few feet of leaving the antenna. Every research team that tried this before slammed into the exact same invisible wall and eventually walked away. Teams could prove the frequency carried enormous amounts of data inside a sealed, bone-dry lab room, but the moment they took it outside, even on a mildly humid day, the signal would collapse within a matter of feet. Picture a garden hose. Widen the nozzle and you get more water flowing, but only if you also increase the pressure behind it. Otherwise, the stream just falls apart a few feet out. That's exactly what kept happening with terahertz signals for years. More bandwidth, but no way to keep the signal alive long enough to actually use it. This is the wall that Chinese researchers, working alongside teams in the United States, South Korea, Japan, and parts of the European Union, have all been trying to break through. This isn't a solo race. Labs around the world have been chasing terahertz milestones for years, and several have hit similar numbers under controlled lab conditions. What makes the Chinese results stand out right now isn't that they're the only ones trying. It's that their specific solution to the water vapor problem is one of the most promising anyone has shown so far. And that fix, the actual engineering trick that let this signal survive, is exactly what we need to look at next, because it's the piece that turns a fragile lab curiosity into something that might actually work in a real city. The fix that changed the game. So how do you stop terahertz signals from falling apart in open air? The answer came from a new kind of antenna array, built out of thousands of tiny, individually steerable elements, each one smaller than a grain of rice, all packed onto a chip about the size of a postage stamp. This tiny chip is the reason the 1 terabit per second speed from our opening even became possible outside a heavily cooled laboratory. Here's the clever part. Instead of sending out one strong signal and hoping it survives, each individual element constantly adjusts itself based on how much signal the surrounding air is absorbing at that exact moment. Going back to our garden hose comparison, this array doesn't just widen the nozzle, it actively repressurizes the stream moment to moment based on real-time conditions in the air. To picture how fast this adjustment happens, think about how your eyes adjust walking from a bright room into a dim one. It takes a beat, but it happens automatically without you thinking about it. This antenna array does something similar, just thousands of times faster and thousands of times per second. That single shift is a huge deal. In earlier lab tests, terahertz signals collapsed after just a few feet. With this new antenna design, researchers held a strong, high-bandwidth signal across a few hundred feet, roughly the length of a football field, both indoors and outdoors, under lab conditions. There's also a manufacturing story hiding inside this breakthrough that's easy to miss. Earlier terahertz test setups needed constant external cooling and power supplies about the size of a small generator just to keep the signal stable for a few minutes. Shrinking all of that down onto a postage stamp-sized chip that runs on a fraction of the power is arguably just as impressive as the speed record itself, because it's the difference between something that only exists as a science experiment and something that could eventually ship as an actual product. It's worth being honest here. This fix works well under the specific test conditions researchers have run so far. It isn't a fully solved problem for every climate, every weather pattern, and every location on Earth yet. There's still real work ahead before this holds up everywhere, at massive scale. But going from a signal dying within a few feet to a signal holding steady across a football field is still a genuine leap forward, and it's the leap that makes everything else in this story possible. There's another honest wrinkle worth mentioning. Even if a signal could carry a full terabit per second through the air flawlessly, most phones and laptops today simply don't have the internal hardware, the storage chips and processors, fast enough to actually capture or use data arriving that quickly. It's a bit like building the world's fastest water slide and then realizing the pool at the bottom is too small to catch all the water rushing down. So this breakthrough isn't only about beaming data through the air. It's about building an entirely new generation of hardware that can keep pace with it. That gap between what the network can send and what our devices can actually absorb brings us to the real test of this whole idea. A lab is one thing. The real world, with its rain, its crowds, its concrete, is something else entirely. And that's exactly where this technology had to prove itself. From lab bench to real-world test, a lab result is one thing. Making it survive the real world is a completely different challenge, and this is where things get genuinely interesting, and where we finally circle back to that humid summer moment teased at the start of this video. In 2024, researchers set up an experimental test bed, essentially a pilot zone, not a full public network, across a stretch of a manufacturing district in Shenzhen, covering roughly 40 city blocks. Choosing a manufacturing district wasn't an accident. Factories are packed with thick metal equipment, concrete walls, and constant vibration, exactly the kind of environment that can wreck a delicate wireless signal. If a fragile lab result was ever going to fall apart, this setting would have exposed it fast. Inside this pilot zone, sustained field speeds averaged around 860 gigabits per second. That's not quite the full terabit seen in the lab, but close enough that engineers called the gap basically a rounding error. To put 860 gigabits per second in perspective, that's enough bandwidth to move the entire written collection of the Library of Congress across the network in under 5 seconds. And it could repeat that every single second, all day long, within that test zone. This matters more than it might sound. In wireless engineering, lab results and real-world results usually don't line up this closely. Real cities bring humidity, foot traffic, concrete, glass, and rain. Everything capable of wrecking a delicate signal. Shenzhen's summer humidity regularly climbs above 80%, exactly the kind of thick, moist air that used to destroy terahertz signals within days during earlier attempts. Holding steady numbers in that kind of humid, steel-packed city environment is a genuinely strong signal for where this technology is headed. One more useful detail from this pilot zone: the new small cells were mounted directly onto existing 5G lamp post infrastructure already installed across the district. That cut projected installation costs significantly compared to building an entirely new physical network from scratch, and crews installed each unit in just a couple of hours using the same trucks and technicians already trained for 5G work. No specialized new workforce needed, which can shave years off how quickly a new technology moves from a promising pilot zone into wider use. So no, this isn't a citywide network you can sign up for yet, and there's no phone plan anywhere offering this today. But a working pilot zone that nearly matches lab performance in a tough, humid, crowded, real-world setting is still a genuinely meaningful step. And that step is exactly what caught the attention of companies and governments well outside China. Which brings us to what happened once the rest of the world got a look at these numbers. The world starts paying attention. Once a pilot zone posts numbers this close to lab results, word spreads fast through the telecom industry. And it did. More than 140 international patent families now reference this style of reconfigurable antenna design, filed across China, the European Patent Office, and the United States. That's a lot of companies quietly betting real money on this direction. Companies don't spend money filing patents on technology they think is a dead end. When over 100 patent families show up across 3 major regions in a short window, it usually means multiple competing companies looked at the same research and independently decided their own version was worth protecting. Major device and equipment makers have started shifting their research roadmaps to prepare for terahertz-compatible hardware over the next few years. South Korea has been running its own terahertz pilot programs in dense urban test zones. Japan and several European research consortiums have terahertz projects of their own, some directly inspired by watching these Chinese field results hold up outside a lab. This is genuinely a global race, with multiple countries pushing hard toward very similar milestones around the same time. Not one country working alone while everyone else watches from the sidelines. Throughout the history of wireless technology, no single country has ever built the next generation entirely on its own. Earlier mobile network generations were shaped by research teams in multiple countries, each contributing pieces that eventually merged into one shared global standard. The race toward 6G looks like it's following that same pattern. It's also worth being clear about the timeline, because this is where a lot of confusion creeps in. This isn't arriving next year. The global body that sets official wireless standards, 3GPP, isn't expected to finalize 6G standards until around 2028. Commercial rollout, actual phones and plans you could buy, is generally expected around 2030. So think of this less as something happening right now, and more as the opening lap of a race aimed at 2030. There are real manufacturing hurdles left too. Early production runs of these tiny antenna chips have reported yield rates below 70%, meaning fewer than 70 out of every 100 chips come out working correctly. For a brand new experimental chip, that's actually a solid number this early on. But turning this into something built by the millions for everyday phones usually requires yield rates above 90%. Closing that gap takes real time, real investment, and a lot of careful engineering work still ahead. This kind of struggle is a normal part of how every major chip technology has developed, and history suggests it tends to close within a handful of years once enough money and attention gets pointed at it. None of these challenges take away from what the lab and pilot zone results have already shown. They simply mark the difference between proving something can work and making it ready for your pocket, and closing that gap is exactly the story that's going to keep unfolding over the next few years. In China and everywhere else, racing toward the same goal. What this could mean for everyone. Here's the bigger picture worth sitting with. Every major leap in wireless speed has followed the same pattern throughout history. It shows up first in wealthy, crowded cities, and it takes years, sometimes decades, to reach the places that could use it most. Rural clinics without steady internet. Schools in remote regions, still waiting for a stable connection. Disaster response teams, working in areas where cell towers are usually the first thing to go down in a crisis. This pattern isn't because anyone is deliberately leaving these places behind. New wireless infrastructure is expensive to build, and it makes financial sense to build it first where the most people and the most money already are. But that practical reasoning is exactly why the gap between wealthy cities and everywhere else keeps repeating itself, generation after generation, unless someone deliberately chooses to close it sooner rather than later. If this new generation of wireless technology eventually reaches those places too, not just the cities that already have everything, that's where it stops being just an impressive number in a lab report and starts being something that genuinely changes lives. A rural clinic with a stable, high-speed connection could bring in a specialist from hundreds of miles away through live video instead of asking a patient to travel for hours. What makes this moment different isn't just that the speed is higher. It's that this level of speed and near-instant response time could let machines, sensors, and AI systems coordinate with each other in ways that simply weren't physically possible before. That's not a small upgrade. That's a new category of what a wireless network can actually do. And it's a story still very much being written by researchers in China and by teams racing toward the same goal all around the world. It's worth remembering that just a decade ago, ideas like remote robotic surgery or fleets of self-driving cars coordinating at intersections sounded like distant science fiction. Wireless technology quietly became the missing piece that turned those ideas into real, testable systems. Whatever comes next in this race towards 6G is likely to unlock a similar wave of ideas that feel impossible today and completely ordinary a decade from now. If this changed the way you think about what a wireless network can actually do, drop a like. It really helps the channel grow. Hit subscribe and turn on notifications too, because we cover stories like this every single week, and you don't want to miss what's coming next. Now I want to hear from you in the comments. Do you think this kind of technology reaches everyday people and remote regions within the next decade, or does it stay locked inside a handful of wealthy cities the way